Look at the surface of any modern printed circuit board. Thousands of microscopic components sit packed together, forming an incredibly dense, layered architecture of copper, polymer, and solder. To comply with global environmental mandates, the electronics industry transitioned to RoHS-compliant manufacturing. This meant stripping lead from the solder and removing halogens from the substrates, forcing manufacturers to adopt materials with lower thermal stability and higher mechanical brittleness. These new materials introduced competing constraints. Lead-free alloys require higher thermal capacity and longer exposure to heat to melt properly. At the exact same time, the new halogen-free substrates are inherently more brittle and suffer from degraded peel strength. This graph illustrates the process window, the operating zone for manufacturing. The lower bound is the minimum temperature required for the new solder to wet the pad. The upper limit is the threshold where the heat begins to permanently degrade the substrate. Because lead-free solder needs more heat, and halogen-free boards tolerate less of it, this safe operating zone has rapidly collapsed. When manufacturing takes place on this razor's edge, a microscopic deviation in a material's chemistry or thermal profile results in complex, catastrophic board failures. When these modern boards fail, standard visual inspections are entirely useless for determining the root cause. A board can look perfectly intact on the surface while suffering from a fatal disconnect inside. Isolating a failure requires deconstructing the board through a strict hierarchy of analytical tools, working systematically from the macrostructure down to the nanometer scale. We have to trace the symptoms through internal structural defects, examine the micromorphology of the metals, analyze elemental contamination, and test the thermodynamic limits of the polymer itself. Finding the physical break is only the first step. To actually solve the problem, engineers must descend into the microscale and reverse engineer the entire thermal and chemical history of the board. The investigation starts at the macro level with a non-destructive spatial mapping of the failed component. High-resolution X-ray inspection, capable of resolving details down to a single micron, maps the internal geometry of dense packaging like BGAs and CSPs. This allows engineers to locate hidden, volumetric voids trapped inside the solder spheres. But X-rays struggle to see flat, two-dimensional separations. For these planar defects, engineers use scanning acoustic microscopy, or SAM. SAM pulses high-frequency ultrasonic waves into the board. By measuring how those sound waves reflect, the system reveals hidden subsurface delamination and cracking induced by that halogen-free brittleness deep inside the FR4 substrate. Acoustic and X-ray tools successfully isolate exactly where the internal separation exists, but they cannot explain the chemical or mechanical reasons why those materials separated. To understand the physical mechanics of the failure, the analysis moves to destructive testing. Engineers perform microsectioning, carefully grinding and polishing down through the board to physically slice directly into the targeted defect. The objective is to expose a cross-section of the intermetallic compound, the IMC, and the specific plating layers, like ENIG, for direct observation. Because these layers are microscopic, observing the structural fracture mechanisms requires the extreme magnification of a scanning electron microscope, or SEM.
This SEM micrograph shows the physical architecture of an interconnect. Right here, we can see a microscopic fracture line propagating entirely through the nickel layer of the pad, cleanly separating the metal layers. Discovering this jagged crack at a microscopic scale proves a mechanical failure occurred. But finding a broken physical structure requires deeper chemical analysis to identify the specific catalyst that created the weakness. We now transition from observing the physical fracture to analyzing the chemical makeup of the specific materials along that fault line. This is done using energy dispersive spectroscopy, or EDS. This spectrum charts the elemental composition of the sample. By reading specific peaks for nickel, phosphorus, gold, and tin, engineers identify exact contaminants or verify if anomalous phosphorus is creating a brittle black pad interface. But sometimes EDS lacks the sensitivity to detect ultra-thin passivation or organic contamination layers. That requires an escalation to X-ray photoelectron spectroscopy, or XPS, which analyzes just the top few nanometers of a surface. XPS goes beyond identifying elements. It measures the binding energy of the electrons to determine the exact chemical valence state. This allows engineers to distinguish between pure copper and oxidized copper at a molecular level. This elemental and nanosurface analysis uncovers invisible chemical impurities that undermine the mechanical strength of the interconnect long before a physical crack ever forms. The final step shifts the analytical focus away from the metallic solder joints and onto the underlying polymer FR4 substrate itself. We have to answer a critical thermodynamic question. Can this specific polymer matrix actually survive the extreme prolonged heat required by the lead-free reflow profile? This chart shows a heat flow curve measured by differential scanning calorimetry, or DSC. By tracking the heat flow, we can pinpoint this exact inflection point. This is the glass transition temperature, or TG, the moment the polymer begins to soften. Engineers then use thermomechanical analysis, or TMA, to track physical dimensional changes, carefully measuring the substrate's coefficient of thermal expansion as it heats up. If the lead-free reflow profile pushes the board past these measured thermal and expansion limits, the substrate will violently fracture internally as the layers pull apart at different rates. By mapping these specific thermal thresholds, engineers can prove exactly when a green board design is thermodynamically incompatible with its own manufacturing environment. Because the modern manufacturing window is incredibly narrow, PCB failures are almost never caused by a single isolated variable. A slight thermal expansion anomaly identified by the TMA exacerbates a minor plating impurity found in the EDS spectrum. These overlapping thermal and chemical stresses compound, ultimately resulting in the microscopic fracturing we capture with the SEM, breaking the circuit. Only by merging acoustic macrostructures, photoelectron surface states, and thermodynamic limits can engineers reverse engineer these complex failures. Establishing reliability in modern electronics requires closing the diagnostic loop between foundational material limitations and catastrophic system failure. As environmental mandates continue to tighten manufacturing constraints, this rigorous, multi-scalar diagnostic approach remains the industry's only safeguard against total system collapse.